So thus far, we have talked about the first three postulates of quantum mechanics. The first postulate tells you that the state of a physical system is described by a vector in a linear vector space. The second postulate tells you that every observable is represented by a Hermitian operator in quantum mechanics, and the Hermitian operator is guaranteed to have real eigenvalues and not orthogonal eigenvectors. And the third postulate that we have discussed tells you that the possible results of any experimentation of an observable will give you one of the eigenvalues of the operator representing the observable. And we've also told you the rules using which you can calculate the probabilities. Okay. So today we will move on and ask what happens after you do the experiment. So this leads us on to the fourth postulate. We have been naming them. This is the fourth in number. So this is the statement of the postulate. If a measurement of the physical quantity A, there is some observable A on the system represented by the state vector psi. Instead of represented, let me say described. Gives the result An, which is one of the eigenvalues of the observable A, then the state of the system immediately after the measurement is the eigenstate corresponding to the eigenvalue An. Okay, so what does this mean? This means that if I actually go ahead and measure it, okay, suppose if before I do the measurement and I want to measure A, I know two things. I know that the results of the measurement should be one of the different eigenvalues of A. If A has two eigenvalues, the result can be either one of the two eigenvalues. If A has 25 eigenvalues, it can be one of the 25 eigenvalues. If I have infinite number of eigenvalues, then the result could be one of an infinite possibility. And I also know how to calculate the probabilities associated with each of these eigenvalues. The probability that I will get a particular eigenvalue is given by the absolute square of the overlap of the state vector of the system with that corresponding eigenvector, right? But what happens after measurement? After measurement, you immediately know, the experimentalist knows that she has gotten the value 10, right? So there is no ambiguity immediately after the measurement. So immediately after the measurement, the state vector of the system, which was written as a general combination, so before the experiment, before measurement of A, the state vector of the system was written down as a linear superposition of all possible eigenvectors of A. So this was given by some alpha 1 times phi 1 plus alpha 2 phi 2 plus blah blah blah, right? Where A acting on phi n is A n phi n, where A is a Hermitian operator. But after measurement, let's say let's say you got A5, okay? Then the state of the system collapses to 5, 5, okay? In other words, the state of the system, the state vector of describing the system, which was some linear superposition of all the state vectors before the measurement, once you actually do the measurement, then the state vector describing the system immediately after the measurement is given by the eigenvector that you have just measured. Okay, so this is still a postulate of intense debate in physics community, in physics research. This is the famous wave function collapse hypothesis. And people are still debating whether or not this is the way to understand quantum mechanics. And those are all different issues. But for our purposes, we can take this for granted that immediately after the measurement, the state of the system is given by the particular eigenvector corresponding to the eigenvalue that you have just measured. Okay, written in terms of the projection operator, this means that the state of the system immediately after the measurement is the projection of psi onto the eigen subspace corresponding to an. This is basically Pn acting on psi. Okay, if this state is not normalized, you have to normalize it properly. If you normalize it, then you get the state Pn psi divided by the length of this vector Pn psi, which is, excuse me, Pn psi, which can also be written as per yesterday's lecture as psi Pn psi. Okay, where Pn is the projection operator. Remember that if An is a non-degenerate eigenvalue, then there is only one state that corresponds to the state of the system. If An is a degenerate eigenvalue, then you are projecting onto the subspace in which the eigenvectors, all of the eigenvectors correspond to the eigenvalue An. This postulate is sometimes called the collapse of the wave function or the state vector. Basically, it tells you that immediately before the measurement, quantum mechanics is highly probabilistic. You cannot really tell which one of the values you would possibly get. But immediately after the measurement, you know exactly what the state vector of the system is. And if I measure A immediately afterwards, if you measure A immediately after, then you get the same eigenvalue An, because the state of the system immediately after the measurement corresponds to that one particular eigenstate, right, among the many possible eigenstates via linear superposition. So let me talk about a couple of cases, and then I will introduce a sixth postulate, and then we will move back to our very first lecture and make a connection with the Stern-Gerlach experiments that we discussed in the very first lecture. Now, what are the couple of comments that I want to make? Comment one. Suppose if you measure not one observable, but you decide to measure two observables rapidly. Okay. So let us say that you have two observables, and these two observables correspond to two operators in quantum mechanics, A and B. And let us say that A and B commute. This means, of course, that they have a common set of eigenvectors, right? So this means that A acting on phi n is an acting on phi n, and B acting on phi n is some other eigenvalue corresponding to, excuse me, the same eigenvectors phi n, because A and B are commuting operators. Now suppose if we measure A, okay, and let us say you get am, then state after measurement is phi m. Then immediately after you measure B. Okay, since A and B commute, you are guaranteed to get the eigenvalue of B corresponding to the state phi m, which is some Bm. Now, if you measure B right back again, you would get the exact same Bm, or you can immediately afterwards you measure A again. And then you are guaranteed to get Am again. Why? Because even though you're doing lots of measurements, you're doing two things. You're measuring them immediately afterwards, and these two operators commute. So the state of the system never has a chance to change. Okay, you're first measuring A and you're getting Am. So the state after measurement is collapsed to the eigenvector corresponding to Am, which is phi m. Since A and B commute, phi m is also an eigenvector of B. So if you measure B, you will get the corresponding eigenvalue Bm. Then if you can go ahead and measure A immediately afterwards, you will get Am. You measure B immediately afterwards, you can get Bm. So you can keep going indefinitely. You can also measure A two or three times continuously and then measure B. Nothing ever happens. You get either Am or Bm, provided that you do the measurements rapidly. You don't give the system chance to evolve in time. Okay, I will explain what this evolve in time means. Comment number 2 is what happens if A and B do not commute. Then of course the eigenvectors of A are not the eigenvectors of B. They are two different set of eigenvectors. So A acting on phi n is An acting on phi m, and B acting on some chi n is Bn acting on chi n. Okay. Now what happens? Measure A. And you get, let us say, same as before, you get Am. Okay, which means the state after measurement is phi m. Now immediately afterwards you measure B. Now obviously this you don't know what value of B you would get. So the way you would actually understand prior to immediately measuring B is that there is probabilities of getting any value of B that you have. So the way you actually do this is prior to measurement, you know that the probability of getting some value Bn is given by the overlap of chi n with the state of the system, which after the first measurement has collapsed to phi m. But after the measurement, of course, after the measurement, let us say, let's say you get some value, let us say bk. Okay, then state after measurement is chi k. Okay, now if I want to measure A immediately afterwards, then prior to my immediate measurement, I only know the probabilities associated with the different values of the eigenvalues of A, which is basically the overlap of phi m with chi k mod square, and so on and so forth. So if the operators do not commute, right, prior to the measurement, you really do not know what the exact value that you would get is. But if the operators do commute, then even prior to the experiment, you know exactly what the value of B you're going to get is, because you know that the state of the system is not a general linear superposition of all eigenvectors of B, but one specific eigenvector of B, specifically some phi n. Okay, so these are the two differences between commuting and non-commuting operators that you have to keep in mind. So before I move on to the next postulate, are there any questions about this? Please ask me if there is any questions or any comments about this particular postulate. If not, I will come back to this again when I talk about the sequential Stern-Gerlach experiments that we discussed initially.
Sir?
Yes, please.
Sir, does this mean that chi k is some linear combination of phi m?
Absolutely. See,
Okay.
chi is a state, but it is also one of the eigenvectors of a Hermitian operator. Phi m is a state, it is also the eigenvectors of a Hermitian operator. So I can always write chi k as a linear superposition of the phi m's, and ulta. I can also write phi m's as a linear superposition of the chi k's. Okay. So I'll give you an example of this when I talk about the Stern-Gerlach experiment in terms of Sx and Sz, but you're absolutely correct.
Okay, sir.
Anything else? Okay. So I will introduce the last postulate, and this is the stuff that you're probably already aware of. My counting is wrong, so it's actually the fifth postulate. Now, what happens if I don't measure things immediately afterwards? What happens if I let the system evolve in time, right? So let us say that I have a box in which I have one single electron and I'm measuring many different things, but this electron is acted upon by some force field, electromagnetic force field. And so the dynamics of the particle changes, right? So the state vector of the system is not the same at all instants of time. So what is the equation that governs how the state vector of the system changes with respect to time? What is the dynamical equation in quantum mechanics? Excuse me. As you well know, the dynamical equation in quantum mechanics is called the Schrodinger equation. The time evolution of the state vector psi of t is governed by the Schrodinger equation. And this equation is given by IH bar ddt of psi of t, the time rate of change of the state vector, is equal to the Hamiltonian operator acting on the state vector. Since this is a very important equation, let me box this since we are doing it for the first time. Okay. Again, this is something you probably already know, at least written in the wave function language. So H is called the Hamiltonian operator. Okay. So this is how I would calculate how the system changes as I change time. Now I can write down the formal solution of this equation. Okay, so suppose if I start at some time t0 and I want to write down the solution at some time t, then I can formally integrate this equation, right? This is a very simple first order differential equation, except that this h is an operator, so you have to be a little careful. But formally, I can integrate this equation and write down the solution. The solution is given by psi of t equals e to the minus, excuse me, IH times t minus t0 psi at t0. Okay. This is the formal solution of Schrodinger equation. Okay. So I will write down, so since I'll be using Schrodinger equation again and again, I will write down time dependent Schrodinger equation. Okay. We will also write down what is called the time independent Schrodinger equation later, but this is the formal solution of the time dependent Schrodinger equation. So I'll make this a little more clear. Okay. Now notice that the prefactor e to the minus h t minus t0 is actually the operator. Okay, it is not a number. It is not just an exponential of a number. H there is an operator. So this is still an operator equation. So the way I would formally guess the solution is by acting psi of t0 by the operator e to the minus ih times t minus t0. Now the exponential of an operator is always defined as a Taylor series. So I can write this as 1 minus ih times t minus t0 minus ih t minus t0 square plus blah, blah, blah. But practically that is not what we do, at least for simple problems. But there are problems in which we have to attack it like this. We will understand what this kind of problems are if we have to understand the formal solution later. But for now, simply take it for granted that this is the formal solution. And this operator, e to the minus ih times t minus t0 is written as u of t t0, and this is called the time evolution operator. Okay. Now notice something interesting about the time evolution operator. U is a unitary operator, simply because H is a Hermitian operator. Okay. In other words, U dagger U would be equal to, simply speaking, this is e to the IH times H dagger times t minus t0 times e to the minus IH t minus t0, right? But since H is a Hermitian matrix, H dagger is the same as H, so this is e to the IH t minus t0 times e to the minus IH t minus t0, which is the unit operator. Okay. So if H is a Hermitian operator, then e to the minus IH is a unitary operator. This is a general statement. If A is Hermitian, then e to the IA is unitary. Okay, you can easily show this is the way you show it. Okay. So this is how the system time evolves. Of course, this is easier said than done. We have to actually solve for this equation and understand how the system changes with how the state vector changes with respect to both time and also XYZ. Okay, so we will talk about how it changes with respect to space and time when we talk about the solutions of this Schrodinger equation. So for now, I will simply introduce a Schrodinger equation as one of the postulates of quantum mechanics, because it really is a postulate of quantum mechanics. It is not a derived quantity. It is something that just has to be supplied to you. Okay, just the way that Newton's second law is supplied to you. But for now, I would like to switch gears, and for about 15 minutes, I want to talk about how the postulates, as we have defined them, help clarify the picture that we discussed and developed in the very first lecture. Okay. Now, to jog your memory, let us go back to what we discussed when we started this course. We started by constructing what are called sequential Stern-Gerlach experiments. So what is a Stern-Gerlach experiment? You let silver atoms escape from a hot oven, and you put in an inhomogeneous magnetic field that has a Z component. And the force that acts on the silver atoms would be given by mu times dB dz. And since mu, the magnetic moment, is proportional to the spin of the electron, of the outermost electron of the silver atom, then the beams would be split according to the spin values, plus half and minus half. So you would have I've drawn in the red color detector over there, two beams on the detector, top and bottom. The top corresponds to one value of spin, and the bottom corresponds to one value of spin, plus minus h bar over 2. Okay. I also told you that in the olden days, this was called space quantization, even though we don't use those terminologies anymore. Now we are constructing a thought experiment, and this is what we did in the very first class. The experiment number 0 was simply one copy of Stern-Gerlach experiment, right? So we supplied a magnetic field in the z direction, and we split the beams corresponding to Sz equal to plus h bar over 2 and Sz equal to minus h bar over 2. Now experiment number 0 was very straightforward. It's the exact same Stern-Gerlach experiment as before. Experiment number 1, we blocked the minus z beam, and we let the plus z beam go through another Stern-Gerlach experiment in the z direction. Okay, immediately afterwards, and we found that the result of this experiment was only the Sz equal to plus 1/2 beam. So let us understand all these things in terms of the postulates. So sequential Stern-Gerlach experiments. Okay, refer August 20 lecture. Okay, I want to simply refer to this because I don't want to keep drawing the figures again, because I'm a little lazy. Okay. Now experiment number 0 is very straightforward. Experiment number 0. So let me write down, now that we know what these spin matrices are, let me write down Sz. Sz equals h bar over 2 times 1, 0, 0, minus 1. And Sx is the other thing that we will employ. Sx equals h bar over 2 times 0, 1, 1, 0. Okay. For completeness, Sy would be h bar over 2, 0, minus I, 0, even though we would not need it for this particular setup. But it's useful to know. Now, how do you understand experiment number 1? Well, after the first beam has passed through the Stern-Gerlach experiment, you're splitting the beam into plus z and minus z. Plus z. So the notation plus z means is equal to Sz equals plus h bar over 2. This is the notation, right? Minus z corresponds to Sz equal to minus h bar over 2. Similarly, plus x equals the beam with Sx equals plus h bar over 2, and minus x is Sx equals minus h bar over 2. These are the corresponding states. And this is the shorthand notation that we have employed in that particular lecture. So experiment number 1 is very simple to understand. After you pass the first beam through the SG apparatus with the magnetic field and the inhomogeneous magnetic field in the z direction, you block out the minus z beam, and when you put the plus z beam in the path of another SG experiment, since the state of the system is Sz equal to plus 1 plus h bar over 2, you're effectively measuring Sz again. And if you measure the same operator again, you are guaranteed to get the exact same result as before. So as per postulate 3, the result of experiment 1 is clear. The result of experiment 1 is you get the exact same eigenvalue and the exact same state as before. Okay. Please stop me if there is any questions at any stage, because the experiment keeps getting more complicated. So this is experiment number 1. What is experiment number 2? Experiment number 2 is you're putting the first beam in the SGZ experiment. So you're putting a magnetic field in the Z direction. You're splitting it into SZ equal to plus H bar over 2 and SZ equal to minus H bar over 2. And now you're again blocking the minus Z component. And in the path of the SZ plus H bar over 2 component, you are now measuring the SX. You are putting the Stern-Gerlach experiment in the X direction. Now remember that SZ and SX do not commute. Okay, SZ and SX do not commute. Okay, in fact, you figured out the commutation relation in your tutorial problem. SZ/SX is IH bar SY. Okay, so this corresponds to comment number 2. Okay, so what should I do? If I measure A, then if I measure B immediately afterwards, and if A and B do not commute, then I would have to express the state after the first measurement as a linear superposition of the eigenvectors of the second operator, so I can compute the various probabilities. So that is exactly what I will do. So in this case, I am measuring, so I will write down the corresponding experiment over here. So this is experiment number 2 that I'm trying to explain. Now I have measured SZ and I've gotten plus H bar over 2, which means the state of the system is SZ equal to plus H bar over 2, which is what we have called plus Z. Okay, this is the state immediately prior to the second measurement. The second measurement, I am measuring the eigenvalue of the SX operator because I am putting the beam in the path of the Stern-Gerlach experiment in the X direction. So how would I know prior to the measurement, prior to the beam splitting into plus X and minus X, how would I be able to understand this quantum mechanically? How would I be able to understand what the possible results are? Well, prior to the experiment, I do not know what the results of the experiment should be, but I know the probabilities. How will I compute the probabilities? Well, I should write the state of the system, which is plus Z, as a linear superposition of the eigenstates of Sx. Okay, and then I should take the coefficients, and the absolute square of the coefficients will give me the corresponding probabilities. So let me write this a little neatly so there is no confusion. Okay, what do I mean? So let me actually work out the eigenvalue. Well, I'll leave it to you to work it out, but I will simply give you what the eigenvalues and eigenvectors are. So Sz is plus H bar over 2, 1, 0, 0, minus 1. The eigenvalues of this, as you well know, are plus H bar over 2 and minus H bar over 2. And the corresponding eigenvectors, you can easily work it out, diagonalize this matrix and find out the eigenvectors. You would find 1, 0 and 0, 1. Okay. Similarly, Sx is plus H bar over 2. Well, this plus here is superfluous. 0, 1, 1, 0. The eigenvalues are again the same as before, plus H bar over 2 and minus H bar over 2. But the eigenvectors of this matrix are different from the eigenvectors of the previous matrix. The eigenvectors of this guy are 1, 1, 1 over root 2, 1 minus 1, which you can easily verify. Simply write down the characteristic equation, figure out the eigenvalues, and plug it in the eigenvalue equation, and you will get these eigenvectors. Okay. So notice that Sx, so plus X state, right? The way I have defined it is basically in the column vector notation, this is 1, 1. Okay. Now I can write this guy as 1 over root 2, 1, 0 plus 1 over root 2, 0, 1. But 1, 0 and 0, 1 are the eigenvectors of Sz. So the way I would write the eigenvectors of Sx as a linear superposition of Sz are plus X equals 1 over root 2 times plus z plus minus z. Similarly, minus x would be 1 over root 2. Well, I'll write it explicitly instead of the brackets. 1 over root 2 plus z plus 1 over root 2 minus z. Similarly, minus x would be 1 over root 2 plus z minus 1 over root 2 minus z. Okay. Now I can invert these expressions and I can also write what is plus z in terms of plus x and minus x, or I can simply look at this. If I simply look at this, I find that if I add plus x and minus x, what do I get? Plus x plus minus x is 1 over root 2, 1, 1 plus 1 over root 2, 1 minus 1, which is basically 1 over root 2, 2, 0, which is root 2 times 1, 0. So this is basically plus z. So I can write my plus z as 1 over root 2 plus x plus 1 over root 2 minus x. Okay, that is pretty much it. Now I have to understand the experiment number 2. Experiment number 2. Experiment number 2 is now very straightforward to understand. The state of my system before measurement is plus z, right? Now, since I'm measuring Sx, I can compute the probabilities associated with measuring plus x or minus x. I know that I will only get plus x and minus x because those are the only two eigenvalues of the Sx operator. But what are the associated probabilities? Well, that is very simple to understand. The probability that I will get plus h bar, let me make this explicit. Probability of getting Sx equals plus h bar over 2 is the overlap of the plus x state on the plus z state mod square. This is basically 1 over root 2 quantity square, which is 1/2. Similarly, the probability of getting Sx equals minus h bar over 2 is the overlap of the minus x state on the plus z state whole square, which is also equal to 1 over root 2 square, which is 1/2. So even before the experiment, I know that the results of this measurement would be two eigenvalues, one with a probability of 50%, the other with a probability of 50%. In fact, when I actually do the experiment, I actually get two beams, one with Sx equal to plus 1 h bar over 2, the 50% intensity, and one with an Sx equal to minus h bar over 2 with a 50% intensity. Okay. So this is how I understand experiment number 2 in terms of the postulates. How do I understand experiment number 3? Well, the first part of experiment number 3 is basically experiment number 2, right? I have prepared the system, then I am feeding it through the SGZ apparatus. I split it into plus z and minus z. I block minus z, and on the plus z state, I am measuring Sx. Again, I get 50% plus x and 50% minus x. Now I'm blocking minus x. Okay. Now in the path of the plus x beam, I'm measuring Sz. So experiment number, what is this experiment number 3? The state of my system prior to measuring the final Sg is plus x. Okay. And now since Sx and Sz do not commute, I have to compute the relative probabilities of finding Sg equal to plus h bar over 2 and Sg equal to minus h bar over 2 in this prepared state. So I have to write plus x in terms of the eigenstates of Sz operator, which I've already done. Plus x is basically 1 over root 2 times plus z plus 1 over root 2 times minus z. Okay. So in this way, since it's a linear superposition of the two states, I know that the probability of getting Sz equal to plus h bar over 2 is the overlap of the plus z on the state of the system, which is plus x, which is 1/2, and the probability of getting Sc equal to minus h bar over 2 is the overlap of the minus z state on plus x, which is again 1/2. Okay, so the results of these experiments, which were actually a little confusing when we studied it for the first time because we did not know the rules of quantum mechanics and the rules of assigning these probabilities. Once you understand the postulates, it's actually very straightforward and very clear, and you know that this is exactly what you should get. Okay, even though you don't expect it classically, because classically you say that if this was a statistical mixture of the two states, then of course, if you have blocked the minus z before, there is no way you can get the minus z again in the last stage of the experiment, right? But you know now, hopefully, after 1 month of quantum mechanics, that this is not a classical mixture of particles. It is not a statistical mixture of particles. But what is operating here is a linear superposition of states. So at every stage prior to the measurement, if two operators do not commute, you expand the state of the system prior to the measurement in terms of the eigenstates of the operator that is being measured. Okay, and then using the overlap of the eigenstates, you can compute the relative weights, relative probabilities of finding every one of the eigenvalues after the measurement. Okay, so this is how you understand the sequential Stern-Gerlach experiments that we introduced in the very first or second lecture, in terms of the postulates that we have developed in the last month. Are there any questions about any of these things? Any questions or any comments about what we have developed thus far? Is this, even though it might seem a little confusing, is this straightforward to understand? Is this okay, or is this still tricky? Any questions or any comments? So we are formally done with introducing the postulates of quantum mechanics. Now, as I promised, I should start in the next lecture by introducing to you the notion of function space, because I don't want to start it now because we don't have a lot of time. In the next lecture, we will get started on the notion of function space. These are infinite dimensional linear vector spaces, and I will talk about operators in infinite dimensional linear vector spaces. Specifically, I'll talk about the position operator and momentum operator. So my goal in the next lecture is to talk about infinite dimensional linear vector spaces, introduce the position and momentum operators, and discuss the subtleties involved in defining the Hermitian adjoint in these spaces. And once we have that in place, we will move on to the subject of understanding what quantum mechanics does for us.